Hello, and welcome to the Agnisys presentation on specification automation for IP and SoC design, verification, firmware, and documentation. I'm Tom Anderson. There are many challenges in the development of today's large, complex IP blocks and huge SoCs. The complexity and the sheer size are definitely one of the problems. There are literally billions of gates, thousands of blocks, and countless interconnections among them that make up a modern SoC. Even the individual IP blocks are very complex. This complexity demands effective reuse with commercial IP across the industry, especially for standards-based IP, standards, of course, used by many different companies. Within companies, reuse across projects, design IP and verification IP from previous generations of a product or from other project teams in the company, and across levels of the design hierarchy from block to subsystem to SoC. Of course, some portion of every SoC will be hand-coded because it will have new functionality that makes it a viable product. Well, you can't avoid hand coding, but it is very time and resource consuming. And of course, you will introduce errors. No designer is perfect. Those errors must be found during verification and fixed before the chip is fabricated. If you think specifically about verifying and developing an SoC, there are some new challenges. An SoC, of course, has one or more embedded processors, so you're now running software along with the hardware. You have more teams involved and duplicate efforts across those teams. The algorithms and the partitioning between hardware and software, generally by an architecture team. The hardware portion, the RTL developed by the hardware design team, verified by the hardware verification team. The drivers, the low-level software developed by the firmware team, and then the entire system, that's hardware and software running together, validated by the validation team, certainly in the bring-up lab post-silicon, but hopefully one does that pre-silicon as well. The process of just integrating the blocks together into the top level of the SoC is huge. Of course, the blocks must all be connected and used properly, and there are literally hundreds of thousands of connections that have to be made, so that alone is a major challenge. If you think about the specification for an SoC, there really is no way today to write an executable specification for an entire chip. So people write them, by and large, in natural language. Everybody understands natural language, but they understand it differently. It's inherently ambiguous. Different teams will interpret the specifications different ways, and many bugs in chips are related to different teams having different interpretations. For example, the hardware group and the software group have a different interpretation of how a particular register might work. There is many different coding styles out there, many different languages, many different formats that are used by the different teams, but they're not unified. And so again, even if you are trying to use executable specifications that aren't linked to each other, you're still going to have problems with inconsistency and misinterpretation. The biggest problem is that that's not a one-time problem. It happens many times over the course of the project. Change is the only certainty in an SoC project. You may have issues in implementation, discovering that you need to go back and change the hardware design or maybe even the architecture. You may discover the chip is consuming too much power for its power budget, have to go back and change things, or maybe a competitor introduces a new feature that you need to respond to. For many reasons, the specification changes many times throughout the course of the project, and every time that happens, there are waterfall effects or ripple effects. The design may have to change and be re-verified. That means the software may have to change, and the entire system may be revalidated, and of course, documentation must be updated to reflect all these changes as well. The solution is specification automation capable of running at the full SoC level. It turns out, although there's no way to write an executable specification for an entire chip today, there are many different formats and many different parts of the chip that are highly amenable to executable specification. For example, registers and memories, probably the first area of SoCs to be automated. Sequences that program these IPs and use the SoC can also be automated. The library of standard IP blocks, the commercial IP we talked about before, can also have executable specs. And finally, the hookup at the top level of the SoC, describing how all the blocks connect together, can also be done in an executable format. And by executable, what do we mean? We mean you can actually generate outputs used by the entire project team. For example, if you have an executable specification for your registers and memories, you can automatically generate at the push of a button the RTL design that actually implements that portion of your chip. You can generate UVM test bench models and UVM sequences to run in the test bench. You can generate C, C++ driver code that programs and uses the IPs and the SoC, and you can generate shared documentation across the project. For custom sequences, you can also generate those sequences in forms that are useful for the test bench, the UVM test bench, the C++ driver code, and again, documentation. The library of standard IP blocks can generate absolutely everything: the design, the test bench, the sequences, the embedded code, and the user documentation. And finally, the description of the chip hookup at the top level can also be executable, generating documentation and the actual RTL code to connect all the blocks together. These generated outputs benefit everyone on the project team. The RTL designers, of course, take the RTL design code, and that represents a big chunk of the chip they don't actually have to go and program themselves. The verification engineers will get the RTL design code to verify it. They'll get help from the UVS test bench models and the sequences to run on the test bench. If they're going to do a co-verification of hardware and software together, they'll also be running the C, C++ driver code in simulation or emulation. The embedded programmers use this C, C++ driver code as the basis for their low-level software, sometimes called hardware-dependent software, interacting closely with the hardware. And the lab bring-up team, of course, no longer has a design or test bench. They have an actual chip back from the foundry, but they will be running the C++ driver code in the lab on that chip in the final stages of system validation. Now, the user documentation generated, of course, is shared throughout the project, so it's very important everybody has a completely always updated, consistent view of what the chip is supposed to be. But in fact, the quality of user documentation generated by specification automation is so good that it's often used by the technical writers to turn into end user documentation for customers of the SoC. Agnisys supports this entire flow with a series of products. Our IDS and ARV products support register memory executable specification and generation of all these elements. ISS supports specification of custom sequences and generation. Spec to AV is a UVM test bench generator that spans registers and sequences. SlipG is our library of standard IP blocks, many popular standards. The chip hookup specification is used by SoC Enterprise to connect together the top level of the design. And finally, we have IDS-NG, which is a specification editor on the front end for the entire flow. And we have DV Insight, a smart editor for system Verilog and UVM. Let me tell you a few words about Agnisys itself as a company. We are the leader in this relatively new area of specification automation. We were formed in 2007, just celebrated our 14th anniversary. We are privately held and profitable, headquartered in Boston, Massachusetts, and we have applications engineers worldwide. Wherever our customers are, we have local support for them. And in fact, we're quite well known for our customer support. We have more than 1,000 hands-on users worldwide, representing more than 50 different customers. And because we have this local application support, we can respond within hours if you have questions about using our products. So in summary, the development of large IP blocks and SoCs is incredibly complex. That's not a one-time problem. You have frequent spec changes and ripple effects, and every time the spec changes, you have to face the same challenges over and over again. So the only solution is to automate every step of the process: hardware design, firmware coding, verification, validation, and generation of documentation. Agnisys solutions handle all this, saving you valuable time and project resources, not just once, but every time the spec changes. Thank you for listening, and I invite you to visit our website, www.agnisys.com, to learn more.